Hello everyone. In this section, we're going to go over the inverse trigonometric functions, arctan, arcsine, and arccos, and we're going to use implicit differentiation to construct formulas for their derivatives, and then we'll just do examples of computations of derivatives involving those inverse trigonometric functions. So here we go. So let's define first the inverse function of tan, the arctan function. So the idea when you're constructing the inverse for a function is you first start with the original function. So for you here on the left, I have the graph of the tan function. So now we want to construct the formula for the inverse of that function. Visually, when you're trying to graph the function of an inverse, what you do first is you take the line y equal x, and then you take your graph and you just simply reflect that graph around that line. If you do so, you will go from the red graph to the gray graph on the right side. Sadly, when you look at the gray curve in the Cartesian plane, that curve is not the curve of a function, because if you look, for example, for some point, if you do the vertical line test, boom, well, you can see that for some x values, if not all x values, there's more than y. There's more than one y value. So we cannot use the gray curve to define the graph of the inverse function. But what we'll do is we'll simply use the middle one. So the middle one, the one that starts at the origin, is going to be kept to define the arctan of x. So that purple curve here, sorry, the magenta curve, that's the graph of arctan. So again, if you start with the graph of tan of x, you look at the line y equal x and you use it as a mirror. The mirror image of the tan of x, the graph of tan of x, will give you this gray curve in the Cartesian plane. But this gray curve is not the curve for a function by using the vertical line test. So what we do, we only keep the middle one to define the arctan of x. So only the middle curve, the one that goes through the origin, is going to be called arctan. So that one only is arctan of x. So if I just take the time to look at it on its own, so the graph of arctan, so this curve is the graph of arctan, we can use the descriptors that we've introduced together. Be careful for notation here. If you see, for example, on your calculator, tan to the power inverse or to the power -1, that's for arctan. It's not 1 over tan, it's arctan of x. So of course, when you look at this curve, now we can describe it. We see that it's defined everywhere, so its domain is R. This function is always increasing over its domain. It's concave up from -infinity to 0, and then it's concave down from 0 to infinity, which means that we have an inflection point at 0. Because the domain is everything, we can compute the limit. We should compute the limit at plus and minus infinity. We can see here that when x goes to -infinity, arctan of x will go to minus pi over 2. So there's a horizontal asymptote at y equal minus pi over 2 at -infinity. And if you compute the limit as x goes to infinity for arctan of x, you also get an horizontal asymptote at pi over 2. So this is just using all the descriptor. You could be a bit more precise too. You could say that the function is negative initially from -infinity to 0. Then we have a root at 0, and then it's positive, strictly positive from 0 to infinity. So once you have the graph in front of your face, you should be very comfortable, like describing it in its entire form. So that's the graph for arctan of x. Now let's do the same thing using the sine function to define the inverse of sine, what we call arc sine. So here in blue, I have the graph of the sine curve. If you draw the line y equal x and you look at the mirror image of that graph, you will get the gray curve on the Cartesian plane, but that gray curve is not the curve for a function. Again, here, if you use the vertical line test, so here we go, boom. So you can see here that there's a lot of x values that will produce a lot of different y values. So this curve fails the vertical line test. So this curve is not the curve of a function, but what we can do is if we keep the portion of the curve from the origin as big as we can, then what we're going to get this purple curve. So from the origin, you go as far as you can on the gray curve, and you try to keep the biggest chunk that will make it a function. And if you do that, you're going to get that purple curve, poof. So not purple or magenta curve. So this portion of the gray curve can be used to define the graph of arc sine of the function. So if I extract this, I just get my arc sine function. So just the magenta one is arc sine. So just that portion. So if I just draw that portion alone, just to focus on it, then what you can do is describe it. So here the arc sine function is only defined from -1 to 1, including the endpoints. It's always increasing. The absolute minimum is at the beginning at -1. The absolute maximum is at the end. The function is concave up when x is strictly positive. It's concave down when it's strictly negative. So there's a change of inflection at 0. So we have an inflection point at 0. Again, once you have the graph in your face, you should be very comfortable to describe this function using domain, increasing, decreasing, concave up, concave down, local min, local max, absolute min, absolute max, and same thing for concavity and inflection point. So that's my graph for arc sine. And as an exercise, I'll let you work on what happens if you start with the cosine function. How would you construct the graph of arc cos in order to define arc cos? And I will let you, once you have understood how to get the graph of arc cos, describe it on your own. So use the domain, where is it increasing, decreasing, concave up, concave down, absolute min, absolute max, and etc. So take the time to describe as much as you can that graph for arc cos. All right, so that's it for the definitions. Now let's compute some derivatives. Oh yeah. Now that we have defined arctan, arc sine, and arc cos, we want formulas for their derivatives. With you, I will construct the derivative of arctan, and I will construct the derivative of arc sine. And as an exercise, I strongly suggest that you do the construction for the derivative of arc cos. At the end of the day, though, what is mostly important with these construction is that you remember their formulas. So the derivative of arctan at the end of the day will be 1 over 1 plus x squared. The derivative of arc sine will be 1 over the square root of 1 minus x squared. And the derivative of arc cos will be -1 over the square root of 1 minus x squared. So just a bunch of new formulas to add up in your basic set of basic derivatives. So anyways, here we go. So for the first one, let's do arctan. So here the idea is we're going to use implicit differentiation, and we're going to use the idea that we know how to compute the derivative of tan. So we know the derivative of tan is secant squared. So now let's use that fact, and let's use the fact that we're building the derivative of the inverse of tan using implicit differentiation to get a formula for arctan. So here we go. So first, we start with our equation. Y is equal to arctan. The goal is to find the derivative of that formula. So first, you just reverse it. So you apply the tan on both sides. So this equation is completely equivalent to tan of y is equal to tan of arctan, which is just x. Now at this point, so now that we have this formula, the goal of rewriting this equation this way is now we're dealing with a tan term. And if you have a tan, you know how to differentiate tan. So of course it's tan of y, so we'll have to use implicit differentiation idea. So if we differentiate on both sides, that equation, so let's compute d dx. So on the left side, because we have tan of something, tan of y, we're going to get secant squared of that something times the inside derivative, and the inside derivative is what we're looking for, dy dx. And then on the right side, the derivative of x is simply x. So that's good. So now the goal is to isolate dy dx. So we just need to divide by secant squared. So we get dy dx is equal to 1 over secant squared. So now what we're going to do is we want to have a formula that is as simple as possible. So we know using the identity that 1 plus tan squared is equal to secant squared, that we can replace secant squared by 1 plus tan squared. So this formula can be rewritten this way. And the reason why I'm doing this is that I know from the second line of my computation, if I have any tan y, I can replace them by x. But now I have secant squared. So if I get rid of secant squared and I rewrite stuff in terms of tan, I have 1 over 1 plus tan squared of y. Haha, and I know what tan of y is. Tan of y is just x. So you get the formula dy over dx is 1 over 1 plus x squared. So all that just to say now that the derivative of arctan of x is 1 over 1 plus x squared. Nice. Now let's do the same thing with arc sine. So we start with y equal to arc sine of x. And we want to find a formula for the derivative. And of course here we know that the derivative of sine is cosine. So we're going to use that fact and implicit differentiation tricks. So if you rewrite this by applying sine on both sides, you're going to get sine of y is equal to sine of arc sine, which is just x. Now that our equation is rewritten this way, we can differentiate on both sides. So let's just differentiate on both sides. So let's derive sine of y. And this will be equal to the derivative of x. So on the left, we have sine of some shit. Okay, so we are going to get cos of that shit times the inner derivative. Of course, the inner derivative is dy dx, and this is what we're looking for. And then on the right side, the derivative of x, as usual, is just 1. So if you isolate y, you get that dy over dx is 1 over cos y. And here, the idea is very similar. We know how to get rid of sine of y. We know sine of y is x, but we have cos of y. But if you use the basic trig identity, sine squared plus cos squared is equal to 1. If you isolate cos in that equation, you get that cos theta. So if I just take the time to isolate it, I know that cos theta is equal to, cos theta, the square root of 1 minus sine squared of theta. So I'm going to use that equation here. So I'm going to use cos. So if I have cos y, this is going to be the same as the square root. Again, the reason why I want to do this, it looks like I'm making it more complicated, but I know how to get rid of sine of y. It's simply x. So it's 1 over the square root. I got my lines. So 1 over the square root of 1 minus sine squared of y. And I know what sine of y is. It's just x, so you get your final formula. The derivative of arc sine is 1 over the square root of 1 minus x squared. Oh yeah. And as an exercise, so I strongly suggest that you try it on your own. And actually, if you just follow the template for arc sine, you're going to get almost the exact same solution, but you can verify on your own. It's a good exercise that the derivative of arc cos is minus 1 over the square root of 1 minus x squared. But again, at the end of the day, it's good to know where it comes from, but you want to also remember that these are now basic formulas. The derivative of arctan is 1 over 1 plus x squared. The derivative of arc sine is 1 over the square root of 1 minus x squared. And the derivative of arc cos is minus 1 over the square root of 1 minus x squared. So let's use these formulas in examples now. So let's compute the derivative of 2 arctan plus 3x4 times arc sine. So if you're computing f prime for that equation, so the first term is simply arctan, so you just have to be comfortable. This is just a new formula, so arctan is simply replaced by 1 over 1 plus x squared. We just keep the 2 in front of it. Then for the second term, this is actually a product, so you have to use the product rule. So You have u for the first term and v. Not going to go over the details, but I'm going to get u prime. So the derivative of 3x4 is going to be 12x cubed times arc sine untouched. So it's u prime v here, plus u, so 3x4 times v prime, and now arc sine is simply replaced by 1 over the square root of 1 minus x squared. So it's just like before, you just have to use those new formulas. Next example, let's compute the derivative of arc sine of 3x plus ex times arctan of sine of x. So we're just mixing up the brand new formulas for arctan, arc sine, and arc cos with previous rules of differentiation. So, but the ideas are absolutely the same. So if you differentiate arc sine of something, so when you're computing f prime for the first term, so you're going to get, so because arc sine is 1 over the square root of 1 minus x squared, now the inside is 3x, so you're going to get 1 over the square root of 1 minus, so the inside now is 3x squared, and then you need to multiply, so a little chain rule here, by the derivative of 3x, which is simply 3. So that's for the first term. You have to use a chain rule here. And now if you use a product rule, the derivative of ex is ex again, times the second term, which is arctan of sine, plus the first term times the derivative of the second one. So here we have arc sine, arctan of something. So you're going to get 1 over 1 plus that something squared. So I'm just going to make it clear first before simplifying it. So that's something, whatever is inside arctan is being squared, times the inner derivative. The derivative of sine is cosine. So you get times cos of x. And that's your derivative for arctan of sine. So again here, really the same ideas as before. You just have to use the new formulas for arc sine or arctan, or eventually also arc cos. And then you can simplify this if you wish. So here we go. So poof, so that's the simplified version. Just brought the 3 at the numerator. 3x, all that squared is 9x squared. And if you multiply ex times 1 times cos, the last term, the numerator of the last term is just ex cos of x over 1 plus sine squared. All right, I'll let you do the other example as an exercise. But for those inverse trig functions, where they come from, how are they defined, and how you compute or construct their derivatives, and how to use their derivatives in more complicated functions involving inverse trig functions. That's it. That's all. Bye-bye.